In triangle ABC with AB is less than AC and AB plus AC equals 2BC, let M be the midpoint of BC. Choose point P on the extension of BA past A and point Q on segment AC such that M lies on PQ. Let X lie on the opposite side of AB from C such that AX is parallel to BC and AX equals AP equals AQ as shown here. Let BX intersect the circumcircle of BMQ, again at point Y is not equal to B. And similarly, let CX intersect the circumcircle of CMP at point Z is not equal to C. And we would like to prove that points A, Y, and Z are collinear. So we start off with triangle ABC, in which AB plus AC equals 2BC. That's just another way of saying that the side lengths of ABC form an arithmetic progression. So we can let AB equal x minus 1. BC is equal to x, and CA is equal to x plus 1, where x minus 1 plus x plus 1 equals 2x. And the only way for this config to happen where AX equals AP equals AQ is if AP equals AQ. Let's call that common length D. So we're about to use Menelaus's theorem on triangle ABC with transversal PQM, which gives that BM over MC times CQ over QA times AP over PB equals 1. But we know that BM equals MC because M is the midpoint of BC, and AP equals AQ because both segments have length D. So CQ equals PB, and this common length is equal to CQ x plus 1 minus D, but that's also equal to x minus 1 plus D. And if you cancel the x's, you'll see that 1 minus D equals negative 1 plus D, which implies D equals 1. And so CQ equals PB equals x plus 1 minus 1, or x minus 1 plus 1, both of which are just equal to x, which is also equal to BC. So we have CQ equals PB equals BC, which implies both triangles PBC and BCQ are isosceles. So let's draw those isosceles triangles. Triangle PBC and triangle BCQ. And upon drawing these isosceles triangles, it appears BQ and CP intersect on the circumcircle of XPQ. But not only that, it also appears BQ, CP, and AX are concurrent on the circumcircle of XPQ. So let's draw in line AX and try to prove our conjecture that they are indeed concurrent on the circumcircle of XPQ. So in order to prove this, we're going to disregard CP for now and simply prove that BQ intersection AX lies on the circumcircle of XPQ. And in order to do that, we look at these angles here, formed by the parallel lines and isosceles triangles. Let's call this point D. Then this angle here, angle XDQ, which is equal to this angle here, angle QBC. But that's also equal to angle BQC, because BC and CQ are both equal to X. And we know that that's obviously equal to angle DQA. So angle XDQ, which can also be written as angle ADQ, is equal to angle DQA, which gives that AD equals AQ. So if D is defined as the intersection of BQ and AX, then it does indeed lie on the circumcircle of XPQ. Now let's define a new point E to be equal to the intersection of PC and AX, which may or may not be equal to D. But let's just call it E for now. And we would like to prove that D equals E. So we again get parallel lines and isosceles triangles. Angle PEA equals angle PCB, because lines AX and BC are parallel. But remember that triangle PBC is isosceles. So angle PCB is also equal to angle CPB, which is equal to angle EPA. And this gives that AE equals AP. But AP equals AQ. So we have AD equals AQ and AE equals AQ. And since both D and E lie on line AX, they must be the same point. And we have proven that D equals E. So now that we've proven D equals E, what can we do next? We know that angle PDQ is equal to angle PDA plus angle QDA. But how else can we express that? Well, angle PDA can also be expressed as angle PCB, but it can be expressed as angle PCM too. And angle QDA, well, by alternate interior angles, that's equal to angle QBC, because AD and BC are parallel. But let's express this as angle QBM, so we can play around with the cyclic quadrilateral angles. So angle PDQ equals angle PCM plus angle QBM. And specifically, if we let the two circumcircles of PCM and QBM intersect at point T that's not equal to M, this is going to equal pi minus angle PTM plus angle QTM. And this is just equal to pi minus angle PTQ. And we know from earlier that this is equal to angle PDQ. So we have angle PDQ equals pi minus angle PTQ. So that also implies quadrilateral PDQT is cyclic, and T lies on the circumcircle of PDQ. So it follows that all three circles, the circumcircle of BQM, the circumcircle of CPM, and the circumcircle of XPQ, all have one point in common, and that's point T. So all three circles intersect at point T, and knowing this, by Michel's theorem in triangle BXC, the circumcircles of BYM, CZM, and XYZ are concurrent at a single point. And so point T, we can say that it lies on a fourth circle as well. And that's the circumcircle of XYZ. I'll draw that in red. So looking at the diagram closely, it looks like AX is tangent to the circumcircle of XYZ. But if you look even closer, it also looks like XT and M are collinear. So we conjecture that they are indeed collinear, and try to prove it. And we're going to prove this collinearity of xt and m by breaking up xtm into two angles, xtq and qtm. T in particular is a nice point because it lies on so many circles. So we're going to break up the angle at T. We would like to prove that angle xtq plus angle qtm equals pi. So xtq is equal to pi minus angle xdq. And angle qtm is equal to angle qbm. And we expect that pi minus angle xdq plus angle qbm equals pi, which is none other than just saying angle xdq equals angle qbm. But this is obviously true by alternate interior angles, so we're done, and xtm are collinear. And that makes it easier to prove our conjecture that ax is tangent to the circumcircle of xyz, because now, knowing that xt and m are collinear, angle axz equals angle zcm by alternate interior angles, because ax and bc are parallel. And that's equal to pi minus angle ztm which is equal to angle ztx, because xt and m are collinear. So angle axz equals angle ztx. That proves that ax is tangent to the circumcircle of xyz. So now we know that ax is tangent, but that actually implies that at is tangent as well, because ax and at are the same length. And since they're the same length, if one is tangent, so is the other. So both ax and at are tangents to the circumcircle of xyz. They meet up at point A, and we would like to prove that that point lies on line yz. And that's none other than proving that quadrilateral xytz is harmonic. In other words, the tangents to the circumcircle of the quadrilateral at x and t intersect on line yz. And that's a common property of harmonic quadrilaterals. They're a special type of cyclic quadrilateral. So all we want to do is prove that the cross ratio of points tx, yz equals -1. In other words, this set of points is known as a harmonic bundle. So we can project from the circumcircle of xyz to a line, and BC seems like the best choice, because xy, xt, and xz all intersect BC at known points. If we project onto line BC, xt intersects BC at M. xx, recall that that's simply the tangent to the circumcircle at x, which is line AX, and that's parallel to BC. So they never intersect. And in projective terms, we call that the point at infinity. So M, infinity, point Y intersects BC, xy intersects BC at point B, xz intersects it at point C. M infinity BC equals -1. That's all we have to prove in order to prove that xytz is a harmonic quadrilateral, which would then prove that A, Y, and Z are collinear. So all we need to prove is this, and this is equal to MB over MC divided by infinity B over infinity C, which is -1. Now, infinity B over infinity c is infinitely far away from both of them. So it's basically 1. So we can ignore this. And mb over mc by directed lengths equals -1. But that's obvious because m is the midpoint of BC. MB is the same length as MC, but in the opposite direction. So we have proven this. We can now say that we've proved A, Y, and Z are collinear as the problem asked us to prove. So thank you for watching this YouTube video. Please follow our channel if you would like to see more videos.